talk about it, and I think it's a really great example of translating the things that we do as basic research scientists and then getting it out literally into the field and out into the hands of the people that can use it most as a way to improve water use and water use efficiency out in the field in the Central Valley of California, as well as the fields in Napa Valley and the wine industry there, which have obviously been suffering from severe droughts over the past several years. So with that, I will turn it over to Andrew, who's going to be talking about commercially viable tool to measure crop yield. So thank you, Andrew.
Thank you. Is that working? Everyone can hear me just fine? Okay. Thank you. Thanks for the introduction and the invitation. It's been a great visit so far. It's this strange stuff falling from the sky was a little bit bizarre to me yesterday, even though I'm from Pennsylvania. It was good to catch up with Mark. I was actually digging through some old pictures to see if I could find anything, and there was nothing appropriate to show in a seminar, so we'll leave it that way. And I brought my own cheering section. My parents actually came for my talk, so thanks for being here as well. So what I'll be talking about today is this project where we were taking what is a research tool and trying to translate it into a commercially viable product. So I was hired by USDA as a plant ecologist, as a physiological ecologist, to help save water in California. I went there very naively with that goal, and I'll tell you a bit about that journey of us taking what was a research tool and turning it into this commercially viable tool. I always like to acknowledge the folks that really get a lot of this work done right in the beginning of these talks. So it's funded by a variety of sources. The initial seed funding for this project actually came from industry. So Jerry Lohr is a prominent wine grape grower in California, and on a whim gave me money to support a really smart PhD student that was working on this. And then that turned into a NIFA, Specialty Crops Research Initiative grant, and then continued funding with the American Vineyard Foundation and other USDA sources as well since then. And collaborators, that this work wouldn't be possible without the groundwork that was laid by Chalta Pau, a biometeorologist, and Rick Snyder, both biomet folks at UC Davis, and then Larry Williams and Mark Batney. And then finally, the people that actually do the work, when we talk about these projects at PIs, the ones that actually get in the field and do everything. Tom Chaplin was the PhD student that we essentially locked in the closet for 3 years, who figured out the math behind the problem that I'm going to tell you about today, and then Chris Perry and Arturo beyond that. So as you're fully aware of, that you've seen in the news a lot, California is suffering from a water scarcity issue. It has historically, and in economic vernacular, this is just when the demand for water exceeds the supply. And in California, we have a lot of demand for water from lots of different entities. So we have a large population that's continuing to grow. This sort of reflects the diversity of California pretty well. In terms of what you see here. You have these municipal water sources of the people here in these areas. I could also add industry as one of these competing sources. Industry in California, when you think of California, you think of the tech sector, and it's actually industry that doesn't require much water. So in terms of water use efficiency, a lot of the competition actually comes in terms of conservation and agriculture. So 80% of the fresh water in California is used for agriculture, for irrigated agriculture. And as you drive up and down the Central Valley, where most of this actually happens, you see these signs everywhere, really illustrating this competition of farmers feeling like they have to convince people that growing food is not wasting water. But there's interesting policy debates here. When you're mass producing walnuts and almonds for export to other places around the world relative to local agriculture and the directions that we're going with this. This has also come under more focus, and you've probably seen illustrations like this in a whole lot of different journals. This is from Mother Jones, of just showing how much water it actually takes to grow different products. So California leads the production of all of these, including walnuts, pistachios. So you don't necessarily think of California as this agricultural basket, but in the Central Valley, it's very productive agriculturally, and it takes quite a bit of water to do it. I'm not advocating for any of these numbers on here, but consumers are actually starting to pay attention to this quite a bit and looking at their water footprint and trying to account for this type of stuff, and this data is actually getting out there. And then on the supply side of things, from the water scarcity issue, is, as Craig alluded to, we've been suffering from historic drought. We did for 5 years. My daughter, who is now turning 6, didn't know what rain was for most of her life, which was a little bizarre to me, growing up in the Mesic East Coast. But at the peak of this, we had most of the state in exceptionally dry conditions. And looks like it's going to continue in this way moving forward into the future. So some geologic record data actually shows that it looks like we're coming out of a wet period historically in California. So we're likely to see more of these extended droughts, particularly with climate change embedded on top of it. And the other thing that we're losing is snowpack. So we have this natural reservoir of water up in the Sierra Nevada mountain range. And so a lot less of that precipitation that's falling is falling as snowpack. And so normally this releases water slowly throughout the season, and we get this runoff of water that then feeds into all of the different sources that we're using. We also have an incredible conveyance system in California where we move the water from the north, where it's running off the hills, going through the delta. This is where a lot of the conservation arguments are coming in, is maintaining flow through the delta for native fish habitat as well as birds that are in this area. And then a lot of that water is pumped throughout the state, getting down to these other areas where it's used for agriculture. And during our last drought, we actually then, the other part of the water equation in California is the groundwater. And we've contaminated this with a lot of nitrates and other compounds through agriculture and other industrial uses. And we started depleting this at a remarkably unsustainable rate during the last drought. And we were seeing this from satellite data that was coming out. So with all of this in mind, I work on sustainable water use. And we do this from the cellular scale and some molecular work up to understanding the whole vine physiology. But what I'll talk about today is really at this exchange between the plant and the atmosphere, and the plant regulating that, and what we can get from that information to give to growers in terms of irrigation management in a practical way. So growers actually use deficit irrigation quite a bit, so they already put less water on than a well-watered crop would actually use. And they do this strategically in many places, like in Coachella Valley, down where this is the desert. It's actually, these grapevines don't go into dormancy normally in Coachella Valley because it's so hot and so temperate all of the time that they have to trick them into dormancy by irrigating in the late fall. This creates an evaporative cooling event where they do it with salt and it drops the leaves and then they bring them back out of dormancy in January. So water is used for that. It's also used for deficit irrigation for enhancing color in the table grape production. Growers in this area can get $40 per basket if they're off 2 weeks earlier. Then if it's 2 weeks later, they get $18 a basket. So anything that can move that production, that maturity of the grapes up is what they're looking for relative to their competitors in these same areas. And then as you're probably aware, deficit irrigation is really important for the quality of wine grapes and generating the colors and the aroma compounds. And it's also being used in almonds during hull splitting to generate the cracking to get the hulls to actually drop off of that. So growers are doing this a lot. They're doing it competitively, but they need better tools to actually track this. One way that you can do this in a water budget perspective is to look at the evapotranspiration. So this is the combination of water that's leaving the system from the soil as well as from the plants. So the transpirational water loss through the stomata. This measurement really integrates the soil plant to atmosphere continuum. So it integrates the roots in the soil, pulling that water through the plant. You get to see the resistances of how the plant is modifying that, and then all the boundary layer parts of that come with the atmosphere plant interaction side. And so growers have been using this concept for a while of focusing on evapotranspiration. And what they need for irrigation management is 2 bits of information. They want to know how much water to put on, so how much has evaporated off the surface and when to put it on. So looking at those stress thresholds. And so the water lost is essentially the replacement need. So are you happy with where your crop is at? You know how much came off of that surface, then you know how much to put back on. And I'll show you how they've done that traditionally here in the next couple slides. But they also really want to know how to detect crop stress. And this is what we've been aiming to do, is how can we do this in a more economically and less labor-intensive way. It's usually done with something called a pressure bomb historically, or other instruments where you can only measure one leaf on one plant in one spot in the field. How can you get a more integrated measure that represents your field in a more cost-effective way? So the way that irrigation management in terms of the ET needs, or how much water was coming off of these plants, historically has been done with the California Irrigation Management Information System, so it's known as CIMIS in California. And this consists of a series of weather stations throughout the state. And you use that data from the weather station to calculate how much water a well-watered grass would use under those same weather conditions that you're seeing in a local spot. So growers use this, and they embed the CIMIS data into, so this is the ET, so the evapotranspiration from that well-watered reference grass under those current conditions is embedded into this equation. So you have your crop of interest here, and you're looking for how much water would actually be coming off of that, and it's multiplied by a crop coefficient. So you take this model grass water use versus what the crop coefficient, your multiplier for a given crop. And the way that these things are calculated is this is a map of those CIMA stations throughout California, and this is an example of one over a well-watered grass, and they're spread out. You can see that you don't get perfect coverage in California from this, though. Growers in this part of the state may be pretty far from where some stations are located. These stations are also not well maintained in many cases, and equipment breaks down, so you get data gaps from this. So they've been looking for ways to do this on a more local level of how they can actually get the same data in that way. And then for the crop coefficient part of this equation, the way that this has generally been calculated is using weighing lysimetry. So essentially what weighing lysimeters are is a giant pot that's embedded into any given field. So this thing goes down 2 meters depth, and you can crawl down and under it. It originally was located on a balance, and they would go in on a daily basis and balance that weight below it. Now it's on a load cell, and so it's continuously measuring the water loss from this crop that's embedded in the normal field. In this picture, you can see that it actually has plastic over the soil. We were trying to calculate how much water was actually going through with sap flow sensors in these vines and isolate the water that was passing through the plant in this example that I have here. So from this lysimeter, you get this water use of your well-watered crop of interest. You divide that by the well-watered grass, and this comes up with your KC value. So you could imagine that there's probably some problems translating this to other places around the state. So issues, as I alluded to before, the CIMA stations are often not well maintained in many places. They're often located far afield from the target field of interest where you're actually trying to do irrigation. The crop coefficient itself is hard to translate from that one lysimeter spot to these other places around the state. And ultimately, one of the biggest problems is that you've taken data from 2 potted vines, these are essentially potted vines in the field, and translated that to every other grape in all of California and used a multiplier for it. And the response of these lysimeters is also not linear to water deficits and other things that we care about in terms of irrigation management. So with that bit of background, what we actually ended up aiming to do was to create an inexpensive and site-specific measurement of actual crop water use. I tried doing this with sap flow sensors when I first got there, abandoned that, and then went for what I'll be telling you about today, is working on surface renewal. And this was developed by a biometeorologist at UC Davis, Chautapahu, and his collaborators in the late 80s and early 1990s. And essentially it's a series of weather stations that would measure the turbulent fluxes across the surface and balance an energy equation that I'll show you here. The key point with this slide that I want to tell you is that since the late 80s and mid 90s, this tool has worked effectively for actually measuring water loss off of plots, but it needed to be calibrated against very expensive research grade equipment, so eddy covariance. So research stations at the high end would cost about $10,000 a piece, which is not economically viable for growers in California and for spreading this out. So the way that this method works is an energy balance equation. If you've been in Craig's classes or Shuei's class, you have likely heard about energy balance in many ways. And what we're doing is partitioning the energy that's coming in from the sun as net radiation. So how much is coming in versus reflected off of that surface is the net radiation. And that energy will then go into 3 main components. It goes into heating the air, so the sensible heat flux portion of that goes into heating the ground, or the remainder of it goes into evaporating water, and that's the latent heat, which we're interested in. So it's been relatively easy to measure net radiation for a while, and you can do this sort of inexpensively. Ground heat flux hasn't been difficult, but these 2 things have been really hard, and this is where, when Tom locked himself in that closet for a while, to figure out the math behind it, he was working on this sensible heat flux. So how is air interacting with the canopy to do this energy exchange, and can we quantify the water that was actually coming out of it? And that's what I'll focus on here, but I'm not going to get into the nitty-gritty of the math. But to just give you a perspective of what this actually looks like, this is a dye study that was done by Chauta and some of his collaborators. And on the top, you have the side view. So imagine this is a surface. It could be a crop surface at the bottom, and you have wind blowing from the left to the right across this. And you see these parcels of air coming in contact. You get a boundary layer effect where the air is slowing down as it's reaching that surface and the air moving across that. And then you get these ejection pulses, and I'll show that one more time, of air actually popping up out of the top of this, of some of these ejections as they come up. And so this is a bird's eye view looking at that. So we're not only trying to do that in this one plane in 2 dimensions, but also in 3D space to actually look at that, how the air is interacting with the surface and doing this exchange. So surface renewal was used to actually get at that sensible heat flux portion of this. And so in theory, how surface renewal works is, I have it described here with these parcels of air, and that's an arbitrary shape that I put in there just to make it look easy. We could argue about what those actually look like and their size. But essentially the idea is that these parcels come in and ephemerally reside in the canopy. So they'll come in for these short amounts of time, and they start to exchange matter and energy with the canopy itself. So this is a parcel coming in that was cooled, it heats up, and then eventually, and you can see that in a theoretical temperature trace, you have a bit of quiescent period where not much is going on. Then you start to get a temperature ramp as you see the increase in temperature. And then the surface becomes renewed, and this is where the idea comes from, is you have an air parcel that comes in, ejects that one that got hotter out of there, and you get a temperature drop at this point. And so that will repeat itself over and over and over again, and it's a matter of whether you can capture these parcels moving in and out of the system. So that's in theory, but this is the real data, and this is what took Tom about 3 years to figure out what the problem was. So where is the signature in this? Is this a ramp? Are these small ones actually affecting this major ramp? How does that impact it as it goes across that time? So without getting into all of the work that was needed for this, he successfully removed, through the math, successfully removed the need for calibration. And I'll show some data that with the actual measurements in the field to show you some verification of this. And I could talk to you more about how we actually got to that point. Ultimately, what the problem was is the surface renewal system in the end was being measured in different experiments with thermocouples. So we have these fine wire thermocouples that measure the air parcel just above the canopy, and they were using thermocouples of different sizes. And so the larger, the thicker thermocouples have a larger thermal inertia. They heat up and cool down more slowly. And so that was actually causing problems across all of these different experiments and giving these different alpha calibrations. And it turned out by understanding the math of where the signature was and looking at those thermocouples themselves, we actually pooled all these values almost into unity when we went back to the original data that was out there by doing a compensation according to the size of that thermocouple. So for people that care about that type of detail, I can get into it afterwards. So we also spent a lot of time, in order to get this down into a commercially viable product, we spent a lot of time getting rid of expensive Campbell Scientific data loggers, started going to Raspberry Pis and Arduinos. My brother, an electrical engineer, built us an even cheaper one based off of Arduino so that we could actually code it in the lab. We were using Peltier plates from computers, sort of recycling old materials that are essentially like a thermopile to measure the flux across this for the net radiometer. We now model net radiation, so we have clear sky for almost all of the growing season throughout much of California. So the clear sky models actually work really well there, and really getting the net radiation is important in terms of this. And then really what Tom's work was to do was to remove the need for the expensive sonic anemometer, which was measuring wind speed and direction, and replacing it with these fine wire thermocouples, which are now out in the field. So we went from something that looked like this and was about $10,000 to this new system. So Tom, the PhD student, started a company. He went through several incubators, and I'll show you that timeline here. We are now down to, in the lab, we make these for about $200 a piece. Tom started Thule Technologies and got this out there. As a federal employee, I can't be part of this company. So I even, well, I'll keep the political stuff to myself in terms of this. But as an ARS scientist, I'm not allowed to do that, but at the highest levels, it's apparently the rules are slightly different. But this was acknowledged at the World Ag Expo as a top new piece of equipment that was coming out, and it's now all over the state. He has about 3,000 of these stations as of last summer throughout varied crops in tomatoes, alfalfa, almonds, walnuts, grapes. We're still doing a lot of the calibration to make sure across several of those that it's working really well. We patented the technology in a joint patent between USDA and UC Davis. I get very tiny royalty checks every once in a while, so I'm cheering for the technology to do better. or maybe my children's college fund is cheering for that. And the fundamental work going from some really understanding what the signature was in this data to an applied results in about 6 years. So Tom put together this team of software engineers to actually develop these stacks. It's now in app form so that growers are actually getting this on their phone. And something I want to point out here is that they have this field stat of where they're actually looking at the crop stress as well as the amount of water that's coming off from it. And I'll get back to this idea of how effectively is this actually working for crop stress as we move on. So we got to the goal of actually giving growers this information in a timely manner so that they can actually make management decisions on it. And the timeline from lab to market, so Craig asked me to touch on this a little bit. We went from this fundamental research with a large SCRI grant, funding this through several ag tech innovation center incubators like a lot of the institutions are now doing. Tom went to an entrepreneurship academy and a venture catalyst. He did an entrepreneurship incubator in Louisville. He won an Ag Start Pitch Fest against his 10-year-old, actually, that he was competing against for another project, which was pretty amusing. I found myself cheering for the 10-year-old during the process. He ended up in the Y Combinator, which is a pretty well-known incubator out in San Francisco. Got $120,000, and then he got his first round of funding from Coastal Ventures in Bloomberg for this of over $1 million. I don't know what the exact numbers on this are at this point. And so we have stations in almonds, grapes, pistachios, all these different crops throughout California. So as a scientific audience, I can tell you all of this, and I sound like a salesperson in terms of giving you this product. But I want to show you actual data that to actually truth this. So we did this work without getting into the math that was behind it. We compared it against that weighing lysimeter, which is considered a gold standard. And we looked at what we were getting off of using our modeled net radiation of the surface renewal system relative to that daily ET that's coming off of the lysimeter. And across multiple years, we're getting very good fits. For field biologists, I was elated with a 0.96 R squared for this, and slopes of close to 1 on these. We also did it. Lots of growers really love soil moisture. Terroir is a big thing in grapes. They love everything about the soil, so they wanted to see these in terms of a soil water budget analysis. We did it across that and found good correlation of what the surface renewal system was finding relative to a soil water budget approach with this. We've also done this more recently, and that lysimeter that had the grapes in it has been replaced with almonds now. And so we're working on almonds at this site, and we're finding pretty good relationship here with this from some preliminary data that we had at the end of last field season. So it's working out pretty well. We've also done it in a variety of different vineyards for the biomet people in the audience. We compared eddy covariance against the surface renewal. And we've now done this in about 20 different vineyards throughout the state, including juice, wine grapes, and table grapes. And we're getting slopes close to 1 in almost all cases, and really good R squareds for this thing. So it's actually picking up the ET really well. The big issue of moving from California to other places is how do you deal with clouds and fog and other things in terms of the radiation. We've been able to do it so inexpensively because we're modeling that radiation. And the key will then be, can we get to a point where we can actually do this in some other ways? So growers always ask me, so this is interesting when you show us data at the end of the field season that it worked, but how are we actually going to implement this thing and put it into practice? And so before Tom actually developed the app and other things, we started giving them examples of this. And ultimately, the first example is if you're happy with where your grapes are or whatever crop that you're working on, this is now like a weighing lysimeter. So we've done the truthing in grapes and in these other crops. It's giving you a weighing lysimeter on site to tell you how much water just evaporated from your crop surface. If you're happy with where it's at, we can give you those numbers. It feeds back into, most growers want one simple actionable number, which is pump runtime. Most growers don't actually make any decisions based on the water itself. Most irrigation decisions in California are about the cost of turning on the pump and the electricity costs. You have some people that will turn it on Friday night because it's off the main power grid usage, and turn it on Friday, turn it back off Sunday night, and that's what they do. It's almost impossible to work with folks like that. But there are others that are looking for data on a finer scale resolution of daily basis. And then the other thing, as the second example, we did an experiment in a Chardonnay plot where we had 3 different irrigation plots side by side by side with large enough fetch to make sure that there wasn't crossover across these plots. And as you look at the cumulative irrigation that's being placed on to the vines throughout the season. So this is across the growing season. And either the cumulative ET is the solid line measured with surface renewal versus what the growers were actually putting on with the irrigation. This was our wet treatment. And you could see that the vines were actually keeping up with what was going on in terms of irrigation for much of that. And then you reached a point where irrigation was far exceeding what was going on. And so we would recommend to the growers that you're overwatering under these conditions, and you should be able to start to see that back here with this signature if the resolution is good enough. Comparing that to a steady deficit condition, what you see with the surface renewal, if a grower is trying to impose some of those deficit irrigation strategies like we mentioned before, they could actually look at what the ET is coming off of this, and you can see these lines staying pretty parallel. So they are at deficit, but not dropping off and getting too stressed and not having enough water actually in the system. And then finally, this is an example in the most severely stressed condition in the dry treatment of these lines starting to diverge from one another pretty quickly with what the surface renewal system was measuring relative to the irrigation that was put in. So we're getting an increasing deficit. So as I alluded to earlier, growers need two bits of information. So they want to know how much water to put on, so the water use, and the crop stress, so to detect this. And so what we thought we would be able to do with this is actually use the ratio of what we're seeing in terms of the ET signature, so how much the surface renewal system is measuring relative to that well-watered grass condition as a potential. So these things should diverge. The well-watered grass will continue to transpire and lose water, whereas the plant that's stressed will be closing down its stomata and you're losing less water to the atmosphere under these conditions. So we started to test this. And normally the way that this is done, is, again, as I alluded to, I got a little ahead of myself before, is growers do it with pressure bombing and pyrometry, soil sensors. These are all point measurements. Irt Sensors is something that's more modern that they're starting to use, or aerial imagery, which doesn't give you quite the resolution that a lot of growers need or the temporal time scale to get at that. So we were wondering about the surface renewal in this case. And we built this idea off of some data that came from the lysimeter originally. So we have lysimeter data for those grapes growing in this versus the water potential. So the more negative value here, the more stressed the plants are. So they're closing down their stomata. And what we found is that the ET measured with surface renewal was dropping relative to that reference ET, and a decent fit for that. And the same thing with surface renewal. It gave us enough confidence to explore this a bit more. And so ultimately during this condition, the vines weren't keeping up with the atmospheric demand of how much water could actually move through there, and it was reflecting stress in the plants. So this is in a plot of Cabernet grapes of showing the black dots are the ET measured with the surface renewal, and the blue bars are the irrigation that was being put into the system. And you can see that you have an irrigation event and the ET is high, and then it starts dropping from this point. You get another irrigation event and a recovery, and the subsequent cycles of this drying and response. So it looked promising in terms of looking at that ET. When we actually measured water potentials, they were more stressed under these conditions relative to after the irrigation event, and you were seeing some recovery. But that didn't always match up. You would have some of these in-between values that were creating problems. And for biomet folks, they might have been like, well, that's not all that surprising to us in terms of using this data. We did this a lot more extensively over several years. We were getting R-squareds between these that were decent in some plots, non-existent in others. And then when we followed it up in those exact same plots the next year, they all went closer to zero. So we started losing some faith in actually using this as a stress indicator. So we then started looking for alternative technologies that we could use to do this, kind of coming from the other direction. So infrared sensors have been used for measuring stress for a long time in plants. This is an infrared radiometer from Irt Sensors, and essentially it's measuring, does my plant have a fever? How is it doing under the condition? Is it stressed? And it will increase its temperature as it closes down its stomata, and it loses that evaporative cooling effect of transpiration through the stomata. And so these have been used since the 70s and 80s pretty effectively. They've gotten more refined with modeling and canopy modeling and understanding the shape of the canopy over time. A lot of these different ones, the main point here is just to show that some of the newer methods actually need a lot more inputs into this data, which make it not so practical in some ways of a stress indicator. But we were still testing this out. And so this hadn't been done in grapevines. We looked at this in grapevines and looked at the canopy, the total canopy stomatal conductance that was calculated from these. and found that relative to actually doing measurements with individual leaves, we were getting good relationships between these as well. And then for the stress index of the water potential, again, more stressed here was showing up in terms of this crop water stress index. So again, feeling pretty good about this. And then what we did on a whim was we actually took some of these IRTs. So we had a stress instrument, but we wanted to see if we could get to how much water with this instrument. So we actually applied the surface renewal math, but to the temperatures that we were seeing from the canopy. So normally surface renewal is measuring the air parcels, and so you have the canopy exchanging energy with those air parcels. So now we're looking at the source of that heat, of looking directly at the canopy and applying the math there. And so applying that surface renewal math using these IRT sensors, we're actually finding pretty good relationships versus these lysimeters. We've now done this for the grapes and almonds and alfalfas. The R-squareds are not quite as good, but still a pretty good fit here in terms of this. So we might have a new technique to be able to get to this. And the reason that this is promising for us in a more practical sense is that you have a lot of commercially available IRT sensors now. These things are in rooms for tracking how many people move in and out of rooms. They're in your cars for looking at the temperature of your Coke can that's sitting in the cup holder. They use them in a variety of different ways. Because of the economies of scale, we have this cheaper sensor technology that's showing pretty good resolution. And we're working with electrical engineers now at Davis to build this into a system to see if we could use this in an equivalent way to what we did with the fine wire thermocouple originally. So this is just some time plots of the expensive $600 research grade Apogee sensor versus these cheaper $60 IRTs off the shelf, showing good resolution. And then when you zoom in terms of what we care about for the ramps, showing similar peaks, but they're offset. And so we're working on figuring out that offset, how repeatable this data is with these sensors, and are you losing some of that calibration? Because what makes these expensive is the really fine-tuned calibration that the company does for these sensors. So we're doing this work. Since the grape no longer has a lysimeter, we're creating our own lysimeters right outside the building at the Robert Mondavi Institute. We have grapes growing in these pots sitting on load cells and a variety of these. And since we're actually looking at the canopy temperature itself, it actually gives us a way to replicate this data and do stress indices as well. And so finally, in conclusion, just to sort of sum this up, we worked at developing something for looking at how much water is actually coming off there. We think we got there with the surface renewal system with the fine wire thermocouple. It's not working quite as well with the WEN, and that's where we're exploring some of these other things. And it's being used already in terms of policy in California. So you have growers that are already doing water trading based off of the data. So I have Jerry Lohr is growing wine grapes next to alfalfa growers down in the Central Coast. He's using only 0.9 acre-feet of water across the entire season. The alfalfa grower is actually using 4 acre-feet of water. That's essentially, imagine piling 4 feet of water up across that acre surface is what that unit of measure that growers like to use. That's how much the alfalfa growers are using. Then the wine grape growers are buying those alfalfa growers out of production, and it's feeding into some policy implications where the state's attorney general is getting in it. This is where you get really scared as a research scientist of how are they actually using this before we've totally tested all of the various factors with it. But I view it as an iterative process. We have to take these first initial steps before we can really make these leaps to get these things in the hands of people more effectively. And so we're really looking at some conditions where we may move towards like Colorado or Israel or other places where they allocate water based on ET demands and ET of whatever given surface is there. And really a lot of this comes down to what are the hurdles to adoption. And this college knows better than anywhere that it's all about the humans when you're trying to get stuff done on the environmental science side of things. My father-in-law is a sociologist, and he asked how some things were going with getting growers to adopt some of this. And I said, you know, it turns out that it has nothing to do with the technology, and it's all about who's turning the valve and convincing each of those people to communicate effectively. And he looked at me and he said, how long have I known you? Why are you just figuring this out now? That after 10 years of this, you're just realizing that it's the humans that are the most important part. And part of that for us is that growers are really scared of things like new diseases and insects that come in, and they're willing to welcome help for that. But irrigation management has been handed down from grandfathers to fathers to sons, and so they don't want us necessarily meddling in that, and they feel like that's something that they actually have under control. So there is a lot of inertia, and it takes a while to get there, but I think we're moving in the right direction. And then finally, just as a plug, I'm involved in a another project where we're trying to do this surface energy balance using data from Landsat and MODIS in a two-source energy balance. I'll talk about this in the guest lecture tomorrow a bit more, of some folks that work on the satellite work in Beltsville. Bill Kustis and Martha Anderson are driving a lot of this work, and we're doing the ground truthing. So using our surface renewal and other crop physiology measurements to make sure that we're connecting what we're seeing from the satellites really effectively and developing some management tools for the growers. And with that, there's a whole lot of people, as I mentioned in the beginning, that have been involved in this that I'd like to thank, and thank you for your attention today.
We have time for a few questions if anybody has any for Andrew.
So you mentioned that one of your concerns when moving from this area to other areas is cloud cover and stuff like that, but it seems like one advantage you have here is that maybe all of the rainfall that comes in or all the irrigation is lost to evapotranspiration. So how does this work, I guess, when you move to an area where you're losing a ton of water to streams and rivers? Does it change things, or maybe it's not as important because in those regions you have maybe more water? Or
Yeah, it's a good question. It's in irrigation management, even in California, the bottom end of your bucket that you're putting the water into is draining as well. So you are draining to groundwater. And so if you're trying to effectively irrigate, you really want the amount of water to be used by the crop itself, as long as you're not dealing with salts and other things. So often growers will be putting more water on to move salts down out of the soil profile and leach that fraction out of there. But it's a good question in terms of slope becomes a big issue for that, and underground flow for some of these conditions. I hadn't thought about that directly of much moving beyond California at this point, so it's a good question. Go ahead.
So I have been following the development of surface renewal for many years, right? So it's really I'm really happy to see that your colleagues are able to commercialize something fundamental about air turbulence to something that can make profit out of. I'm following up on Pete's question that how you might be able to extend the technology to other parts of the world. There are many parts of the world that actually have similar climate to California, Western China, Australia, Israel, and maybe Colorado as well. So I think the technology can be just moved over there and be used. Maybe there's other type of hurdles. I wonder whether you can comment on. Let's say if you want to sell this product in Australia, what would be the first step?
Yeah, I've totally ignored that. So I was at a breaking point here in my career of where I was going to leave my job. I actually had my wife on board with me leaving to go do this. And when you go and approach startup folks about money, anyone as expensive as me, just because I have 2 little kids and I was unwilling to take a salary cut to actually go on this adventure and leave what is a really fantastic research gig at UC Davis. It was a lot of soul searching in terms of what I was going to do. So I thought a lot about the business side and those translation. I think it would be partnering with other researchers in those places to do that effectively. I think in terms of the radiation stuff, we can do ground truthing of that by having fewer stations. If that's an expensive component, you may be able to have one that serves several stations close to that one area that you're actually working on and get a decent radiation budget with that. The other part comes from partnerships. So we're working with folks from Israel and Jordan and Syria as well, and through sort of the US BARD proposals and things like that of developing through the technology side of it on the competing side. But when you're dealing with patents and other things, I learned way more about patent law than I ever thought I cared to know about it. And that becomes a huge hurdle for a lot of this stuff. I don't know if I answered your question. I was very scared of your questions anyway coming here, so as a plant physiologist, and to have you as a biomet person in the audience. So thank you for asking a kind one that I could evade effectively.
Is this on? All right, yeah. I have kind of 2 related questions. I promise they're related. It's not a way to sneak in, too. Okay. But, have you ever thought, and maybe you are doing this, but incorporating more of a Bayesian analysis where each measurement tool is kind of learning from its own specific site and kind of adapting the measurements as it goes along and taking into account that information, prior information essentially, and kind of moving more into an automated process? And that's kind of my second question is, how automated can this get, and would it go so far as to be able, the app could just turn the pump on when it needed to, and then the farmer or the grower essentially wouldn't it be as needed, I suppose, which could then, I suppose, pose a threat in terms of the human dimension as well, like the practical knowledge they have on their land. This app could be seen as threatening that, or this kind of these exact measurement tools.
So yeah, those are great questions, and they touch on sort of this dilemma that I had of potentially leaving my job to go do this. Of when I was thinking about the long-term adoption of this, are we creating a tool that ends up ground truthing other tools so that we would become obsolete pretty quickly? And there's the fear of that through Bayesian analysis or other things, ground truthing satellite data, which is going to be much more readily available, especially with a lot of the commercial satellite companies coming online. That was actually one of the things that kept me in my job, is the worry that would be replaced pretty quickly by a lot of the mathematical tools that could do that type of thing. And then to your second question of, yes, that is the absolute goal of getting this to link to the pump, but eliminating the human, and there's jobs involved in that. There's somebody that gets paid to go out to turn those knobs. And even when we're doing an irrigation trial in a vineyard, the manager that we talk to often agrees to do something, but the person that actually is in charge of turning the valve doesn't feel comfortable with the numbers we gave them. And essentially it's their butt on the line there. And if the crop fails, then they're going to be the one that gets fired. So they don't know who I am, and I'm communicating with someone else. And it's that lack of effective human communication there. So the technology folks would love to go directly from the phone right to the, or from the server directly to the pump. And that's possible. So all of that equipment is available now with cheap pumps that you can actually relay information to the pumps as of today. So Netafim and other companies are doing that. You're all out of questions.
Yeah. So you mentioned at the end that the grape growers were using half a foot or something, and the almond growers were using 4 feet, and partly due to some of this information that they're starting to trade, or the grape growers are moving in and using some of the almond. But that's information we've known for a long time, right? I was wondering if you could just talk a little bit more for this audience about the process of why it took so long for us to realize that growing grapes is better with water, and we should move more towards that in this area.
Yeah, that's probably going beyond my history in that, but yeah, you mean in terms of why we doubted the data that was actually out there? Or?
Well, I mean, it's that actual number, like you didn't need these instruments to demonstrate that, right? They demonstrated at a fine scale.
Yep.
So why is it taking so long, I guess, for...
Yeah, part of it is a lot of private information of people not, but it's available in different ways, but there's a lot of that's not, folks aren't willing to share those exact numbers from the irrigation bits that come out from that if they're not required to, based on what they're getting in terms of their allocation. So that has definitely been a hurdle to that. Yeah, I don't know why. You're right in terms of this data does just back up what we've known for a while from that, but something about people seeing it for themselves on their plot ends up making a difference, and I think there's something to like the visualization of an actual number in hand where some independent person comes and evaluates that. I don't know if I'm getting to...
Okay, that's good.
Yeah.
Hi there. Thanks so much for your presentation. I had a question about the last point you mentioned, which is that ultimately it's humans that are the most important link in this technology adoption. And so in your research in the communities that you've worked with, what would that body be, or who would you be interacting with? Would it be an extension agent, or who would be that person to help with this adoption? Thanks.
That's a good question. There's a variety of different people. So there's been some studies done out there of who are the sort of hubs of knowledge and the effective communicators, and specifically study that in the grape communities. A lot of it is A whole lot of work happens by looking over someone's fence. So what is the neighbor doing, and is that person making money? They will mimic what the neighbor is doing. And so assuming the soils and things are pretty similar in those conditions. And so there's a lot of that. The farm advisors certainly are a credible source of knowledge for these folks. A lot of it is private consultants that have come in and established themselves over a long period of time and developed a rapport with folks. So it's different conduits, and it depends on the company, and it depends on the scale. In wine grapes in particular, you have everyone from Gallo, who is the leading producer of grapes in the world in California, down to growers in Napa that have a half acre, and they're making $100 or $200 bottles of wine. And so in that case, you're talking directly with the owner, versus Gallo, where you can make a much bigger footprint. You're talking with the leadership at Gallo for some of those. The nice part for us in Gallo, the person that's running a lot of this was an extension specialist in our department before he got hired away by Gallo. So he gets that communication side. He gets communicating with growers and with researchers.
Okay, last question. So I'm just wondering if you could speak to your experience in terms of this proprietary information that just came up. So some of the questions we work on with soil health, there's huge amounts of data out there on yield and nutrition for crops, which is all privately owned, which companies are setting up and collecting and providing back to farmers. But a lot of it has strong environmental consequences beyond the actual farm scale. So the same exactly with what you have with the water. So did you, when you were thinking about this business model that you didn't go down, were you having thoughts about whether those data would be open access later on so that you can use them for purposes other than just perfecting the particular kind of the crop yields? Or was it just about money?
Well, so let me explain that. So we had a grower that took us out to dinner, and he said, if Andrew's on the team, I'm putting in $1 million tonight to do this, and I expect you guys to be generating $10 million of revenue per year within 5 years if you're doing this effectively. This is a grower that is the single largest table grape grower in California and has holdings in Chile and Australia and other places. So going home and looking at my children, it was hard to not think about the lottery ticket that was sitting in front of me, but there's a lot of hard work to actually get to that payoff. So there was the money side, but as a researcher, I was actually advocating, and part of the negotiation broke down, is I wanted to do this as a free tool. And Chauta was advocating for the same thing. He said this should just be publicly available. We should do it like CIMMYS. We should make these stations. We should get DW, the Department of Water Resources, to pay for it. We put these stations out there and everybody benefits from that. And those were the competing ideas that we had. And with that would have come an incredible data set for us as researchers. I am now trying to get access to that and not being able to break through sort of that wall. Even if we do it anonymously, growers are not particularly comfortable with us taking that data and even feeding it in on a regional scale. So they're just very protective of this stuff because they think it's going to be taken away from them. And if people really know what it costs. The grape growers, though, as you alluded to, are coming out looking very good compared to almost everything else out there because of some of these quality parameters that they go for with deficit irrigation. And almond is really in the crosshairs in the news and policy-wise in California. And the nice part is they're dedicating money to actually test some of these things because of it. So, yeah.
Okay, well, thank you, Andrew. And,
Thanks. Thank you. Hi. Yes. Yeah, certainly is it INTA or IRTA in Spain? I think it's INTA. There's a government research agency that is doing similar stuff. If you send me an email, you can ask Craig Roachson for my email, or I can even give it to you now. I just put that one in there.
Cool. Sweet.
I can definitely connect you. There was actually a woman that works for Gallo now. She's from Spain originally. She was doing a lot of the satellite work here and then got hired by Gallo in terms of their irrigation management. And then there's another guy, Joaquim, who went back to Spain and working at this group. So there's a lot of people embedded in the same group that are kind of doing things across scales. Yeah, exactly. Yeah. Your name is? Alberto. It's good to meet you. Okay, I'll look for your email about them. Or do you want me to write it down for you? Or? Yeah. Yeah, we can do it that way. Okay. For a graduate, yeah. You can still work in both places, right? Just be creative about where you do your work, right? Yep. Yep. Well, there's possibility for other people to get embedded in the GrapeX project as well. So if you have sort of funding to support yourself to come out to be parts of projects, that's also something that could be explored, right? And just because you're here for school doesn't mean that you can't study systems other places like so many people do. So it depends on with your advisor and things like that. So yeah. Yeah, good to meet you. Okay, sounds good.
That was great. Thanks.
Thank you very much.
Yeah.
Yeah, you coming up here for a lecture?
Yeah, I was at the seminar before that. I went to a seminar in engineering on sensors, and yours was better.
Thank you.
Yeah. I think I'm going to ask everyone to tighten it up for class because I'm going to try to put my camera on where Arthur